come for some, practically we'll see that in general. So if you look at the conductor, let me introduce all the practically we'll analyze this. Huh? Till now what happened, I just assume that only temperature change, what happened, the change in temperature will change only the resistivity of material. But practically what will happen is, this is a length, this is the area of cross section, then this is resistivity. So we know, now as I, this is at 0 degrees Celsius. So if I rise the temperature, so what happened to resistivity will change. What happened to length? Thermal expansion should occur. Area of cross section S will change. So almost all parameters will change. No? So there are two things are there: alpha R, coefficient of thermal resistance, then alpha theta, coefficient of thermal expansion. Both things will come into picture. No. So can you bring expression for the change in resistance? So earlier, what discussion, we confined ourselves only to the change in the resistivity of material. And what happened? We discussed here. Now practically, if I vary the temperature of conductor, the length will change, area of the overall the conductor will expand, it will undergo volume expansion, length, area of cohesion will change, and the resistivity also will change. So how now the change in resistance will be related on both these parameters? We have to bring an expression. So I'll proceed with the mathematics. Resistance R is equal to rho L by A. So I'll differentiate now. This will be dr. I'll give 2 minutes time. If you want, you can try it. You know enough of some mathematics, no? I'll just give 2 minutes time. Let's see that how things are related finally. If I rise the temperature, I'll vary the temperature of this conductor. The resistivity, length, area of cross section, all will change. All three quantities are variable, no? Here. I have water, so meanwhile you will try it. Now let's differentiate this. dr is equal to L by A d rho by dt. So shall I'm varying with the temperature, no? So dt, I'll write it, plus rho A dl by dt. Capital T is a temperature. T indicates temperature. Then rho L outside. So dA by dt. So this will become minus of 1 by A square dA by dt. Let's simplify the equation. Now few things will write it. What is dl is equal to L alpha theta dt. What do you mean by dA? dA should be equal to A into 2 alpha theta dt. Then what do you mean by d rho? Rho into alpha r d theta. So let me substitute all the things. So dr by by dt, L by A, d rho by dt. D rho by dt should be rho into alpha r, rho by A, dl by dt, L alpha theta minus of rho L by A square, dA by dt should be equal to 2A alpha theta. Rho L by A alpha r, rho L by A alpha theta, rho 2 rho L by A alpha theta. So rho L A alpha r minus rho L A alpha theta. So this will be rho L by A alpha r minus alpha theta. So this is what dr by dt. Further, what is rho L by A? Should be equal to r, the resistance. Or generalized thing, delta r is equal to r into alpha r minus alpha theta into delta t. Usually alpha theta will be very much less compared to alpha r. That's why in all our numericals, we didn't bother the thermal expansion of the material. I think there are these two are two different parameters. The overall, the parameter, we know that as you rise the temperature, the material must expand. The distance between any 2 points on a material must increase. So because of that, the resistance also must change because the dimensions will change. And what is the alpha? Alpha is something related to collision of drifting electrons with the atoms. So that the phenomena totally are two different here. This is something alpha theta corresponds for what? Change in the distance between any 2 points of a conductor. It will show that particular effect is what we are reflecting here. What is alpha? Alpha is something about the collision of the drifting electrons with the atoms. When we compare both, practically when I check it, no, the alpha theta will be very much less compared to alpha r. That's why in all our resistor problems, we didn't bother to consider the changing dimensions of the conductor due to change in temperature. Because when you are measuring the change in resistance, alpha theta, practically it will be very much less than r. That's why. So we started our discussion with only the alpha r, that one. Are you getting the idea now? So why we didn't bother? If you no sir, I want to consider, then bring the problem like this. Then bring this equation. So if you're considering even the thermal expansion of the material also, this should be the formula. Without thermal expansion of material, delta r equal to r alpha r delta t. Okay, this is about. So now what is alpha for a metal? So this is called a coefficient of temperature coefficient of resistance. And this alpha will be positive for metals, for most of the metals like copper, aluminum, all. And alpha will be negative for some materials like a thermistors, semiconductors. There, what will happen for alpha? Why alpha positive? Any reason what we can give? As you rise the temperature, then what will happen? The collision of the drifting electrons with the atoms will increase because of more number of collisions, more resistance is applied to the flow of charge. That's why the resistance increases. Therefore, the alpha is positive. For some metals, for some like even semiconductor also is a metal only. We'll call this a semiconductor rather than conductor, like a germanium. Example of semiconductor, germanium, silicon, gallium arsenide, all these are called as semiconductor materials. A good example of that is germanium and silicon, I'm telling. As you increase temperature, what actually happens in this material? As you increase temperature, the resistance will decrease. That's why the alpha for them will be negative. So how you have to show alpha? Now the rho is going to be decreasing quantity. Here the rho was increasing with the temperature. No, the rho will be decreasing. The graphs for these two will be in detail in semiconductors. We are going to learn. Time being, I'm just giving information. They are called as thermistors. Is there? So as we discussed like this was the some rough graph. I'm giving it here. As you increase temperature, the resistance will decrease. Any reason for that? As you increase temperature, the concentration of free electrons will increase. In case of conductor, the free electrons, the concentration will be very less, very small change will come, very small increment will come, but the tau will dominate. The tau will decrease. Because of that, the rho was increasing. This is what happens in conductors. In case of semiconductor germanium, the tau, what happened? The eta will dominate. Eta will increase by large amount. So the resistivity will decrease. So can you remember rho equal to, we brought ME by, I'm just discussing all the concept, like what all we discussed, no? I'm just analyzing with the help of this one only. In case of metals, the effect of eta is almost negligible. The tau decreases, that's why rho increases. This is what happens here. In case of the semiconductors, the tau, though it changes, but it will have negligible effect. But the eta output will increase by large amount. The rho will decrease. The conductivity, what's happened itself will increase here. So or better call eta here. The charge conductors, the number of charge carriers will increase. In case of thermistors, so they'll have negative temperature quotient of resistance. Okay, fine. So there's about some theoretical questions that are asked even in SCORM also. You are supposed to remember this data also. This is something very important both in NCERT, even in SCORM, he has stressed it. I just close it, just you remember some database problems similar to like thermal expansion. We'll go for next hour, the application problems here. How to find out the resistivity of different shaped conductors. Different shaped conductors means like already we have discussed some cylindrical and tapered rod, no? So let me go for, and also thick sphere also we have discussed.